Okay. Lesson 6. Limits and continuity. Some more limits. Shocker, right? Everything in Unit 1 is going to be limits. Okay, so now we have an understanding of limits and using limit notation. We can use limits to define continuity at a point. This is a very important concept throughout our course. You already know the basics of it because I've talked about it. If a graph or if a function is continuous, what do we know in terms of limits? We've talked about how the limit from the left and the limit from the right have to meet. And for it to fully be continuous, the graph also has to exist at that point. Okay, like the value of the graph at that point has to be the same. Okay, so that's the kind of the idea of what we're talking about. We've talked about a little bit, but officially to define a function as continuous, that's what we have to be able to show. So, use the graph below to complete the table. You should look for 3 conditions that are necessary to satisfy the definition of continuity. That is, what 3 conditions must exist in order for f of x to be continuous at a point x equals c. I'm trying to remember how they have it defined. Okay. So, as we think about this, if something is continuous, trying to decide how I want to think about this or how I want to lead you here. We talked about how the graph must exist, okay? So, for instance, for something to be continuous, what is that point at? -3? Is my graph continuous at -3? No, why not? Okay. There's a hole, and where is the point?
-6.
The point is down here. If this is continuous here, that point has to be up here, right? And that's where we can talk about that it has to be defined at that point, okay? So one thing I'm going to put here is that f of c is defined. Okay, so the function at point C. So C is some number right here. So if we're talking about the limit approaching 3, then f of 3 must be defined. Okay, there can't be a hole, in other words. Okay, the limit from the left must equal the limit from the right. That is a simpler way of saying that the limit must exist. Okay, so we're going to say here the limit as x approaches C of f of x must exist. Okay. And the third piece is that limit has to equal that point. So the limit as x approaches C of f of x has to equal f of c. Okay, those are your 3 official pieces that when we're trying to talk about is a function continuous. Okay, does it meet those pieces there? Yes.
So at x equals -3, is that just a hole, or is that considered a jump? Since
it's a hole there with a, it's a hole. It's not a jump. A jump is more what happens at -5,
okay,
where the graph stops somewhere and picks up somewhere else. Okay, that is a hole because the limit is the same on both sides. It just doesn't exist at that point.
okay.
I was trying to think about what it's called with that being down there, and I don't know if I have a specific name there, but yeah, I mean it's not continuous. It is a discontinuity there for sure. Okay, let's go down and look at this chart. I did not blow this up and make it bigger because I wanted to have that chart there so we could refer to it. But okay, x equals c. We have all these different values. We're going to look at this graph. Find the function value if it exists for the given x value. We're going to find the left-hand limit, right-hand limit, general limit, and then we're going to evaluate, is it continuous? So, when x equals 9, what is the function value?
3.5-ish.
I have 3.5 written down. Okay, so 3.5. We could say 3.5-ish, but we're going to just assume 3.5. Find the left-hand limit. As my graph approaches 9 from the left, it is at 3.5. Find the right-hand limit. D and E, because the graph doesn't exist on the right to approach from the right, does it? So that makes the right-hand limit D and E. What's that make about the general limit? Left and right don't equal, so that makes this D and E. Now, is F continuous at C? So is the graph continuous at 9? And what it comes down to is it depends on what domain they're giving us. Okay? What we're going to say here is it's continuous from one side. Okay, so I have one-sided only, yes. Meaning, so like if we're talking about this function and this function only is defined from 9 to -9, then yes, this is continuous all the way up to 9, and we could say it is continuous. If the domain is all real numbers, and this graph ends at 9, then it's not continuous from both sides of 9. So it really just kind of depends on how the domain is stated there. Okay? So kind of a tricky one. Okay, you guys ready to look at 4? Find the function value if it exists at 4. So what am I going to put? D and E. Okay. Find the left-hand limit.
Infinity?
Why is it 9? It's an asymptote. It stops it and go up.
Oh, it does stop.
9 at 3,
Oh, yeah.
but then there's nothing past 3.
D and E.
And why is it D and E then?
It doesn't.
Because that graph stops at the ordered pair 3, 9. Does it then continue to approach 4?
No.
No. So it's because this is an endpoint, not an arrow. And if you're a little confused here, then look at the right. What about the limit as we approach from the right?
Infinity.
That one is infinity because there is an arrow and it's going infinitely up. So what about the general limit?
D and E.
Does not exist. Is it continuous?
No.
Once. Oh.
Does my graph connect?
No.
This is in the middle of the graph. My graph does not connect. Even if that one on the left went up, it still wouldn't be connected. So not continuous. That is, the limit from the left does not equal the limit from the right, does not equal the value at the graph. Right there, there's an asymptote. No way can it be continuous because the graph right there, the value doesn't exist. So that right there ruined any chance of being continuous. Okay, what about 3?
9.
What about the left-hand limit?
9.
What about the right-hand limit?
D and E.
What about the general limit?
D and
Is it continuous?
E. No.
Just more needs said there. I don't know. Okay. We had this 0.39 from the graph approach 9 from the left. From the right, the graph doesn't even approach 3, does it? Because it approaches 4, but 3 to 4 is just nothing. Okay. And then, so that means the general limit does not exist because it doesn't come from both sides to meet at 9. And that means it's not continuous. Yes.
So there was an arrow there, it would be 9 from the right too in the general limit. Is that correct?
Yes.
Is that my point?
Yes. If that had been an arrow like on the other side, yes. Okay, x equals 0. What is the value there?
6.
What is the left-hand limit?
6.
What is the right-hand limit?
6.
Now we're all the devil. Okay, what's the general limit?
6.
Okay, now Mario's not the devil, right? I don't know. Okay. Is it continuous?
Yes. I beg to differ there. Somebody go get some more.
Are we talking about the devil comment?
Yeah.
Okay, just don't. We're not going to get sidetracked on that.
Sorry.
Okay, x equals, I shouldn't have said, even thrown it out there, honestly, but I couldn't resist. X equals -3.
Danny.
-6.
That's what I put, but I didn't know if it was right. All right.
That's a solid number.
Yeah. That's
The function value
There's the two.
for the given x value. So that graph exists at that point,
Oh.
-3, -6. If that dot wasn't down there and there was just a hole, then I would go for D and 8. But because we have the removed dot, we do. Okay, left-hand limit.
5.
We with them?
Yep.
Yes.
Right-hand limit.
5.
5.
General limit.
5.
5.
Continuous.
Nope. No. This is a hole.
No, because of the -6. Well, okay. Accusations are flying here. Okay. X equals -5. Where are we at here? What do we have?
Negative.
-2. Left-hand limit.
Negative.
Right-hand limit.
7.
7.
See that? We're approaching up high there. General limit.
Danny.
Continuous.
No.
No.
We got too much going on there.
Ooh, that was a lot. That was fun.
Okay. Okay, do we all have what we need on that page?
Yes.
While limits told us where a function is intended to go, continuity guarantees that the function actually made it there. So again, if something is continuous, the limit from the left equals the limit from the right equals the value at that point. They all three have to be the same there. Okay, classifying discontinuities. We have several, and this is kind of what we talked about a little bit last week, kind of what Doug was asking about a little bit earlier. On the first two, removable, we hear them as removable discontinuities or point discontinuities. It's fancy ways for saying they are holes. And you notice there it talks about two-sided limits exist. So as we approach 1, both of these are, as we talk about 1, yes, the limit exists there, but it's not continuous, right? Limit exists, but it's not continuous. Okay, those are removable or point discontinuities. I have a note written in my notes that mentions you could also have the point defined elsewhere. So this would still be true, like what we talked about on that previous page, if you have the hole there, but that point down there, same thing is still true. Okay, so with or without that point being there. So those are point discontinuities because graph does connect on both sides. Okay, jump discontinuities. Okay, this falls into, and I don't know that we've ever classified it, it is a non-removable. It falls into the same thing as an asymptote. And with a jump discontinuity, it's one-sided limits. We can have the limit from the left or the limit from the right, but we can't do the limits together. Okay, limit from the left, limit from the right. There is some visible gap here that you have to jump between. Okay? This one would technically not be a function because only one point is filled in. And I don't know, I don't have any notes in mine. You know, normally we talk about functions. If it's a function, then one of those points would be filled in. Does it have to be the top one that I just randomly filled in? No, it could be either or. Okay, this one would still pass my vertical line test, so like this one would be a function because everything exists and there's one of those 2 points existing there. Okay, infinite, these are your vertical asymptotes. Okay, at least one of the one-sided limits doesn't exist. So, I mean, here's your typical asymptote that we're used to talking about. Here is more like what we just saw in that example where you have the asymptote, but then you also have a point going there. Could that really be, though? I feel like that would have to be a hole right there, but it's not shown as a hole. I don't know. What's the typical one we see? This is a typical one we see, right? What, you know, if it's an actual equation, it's going to look like this. Huh?
Would it pass the line test?
I don't know. Because they're making this look like a vertical asymptote. But if it's a vertical asymptote, then that should be a hole. So I don't know. That's a weird one. Sometimes there's weird examples just thrown in to make a point. And so there's times I have to learn to just kind of not analyze too closely there. Yes?
So what would an example of what the middle top box would look like? Like the, you said it's not a function, so like what would the like writing look like?
In terms of what they would call it,
Like if they gave us like the equation, and they wanted us to graph it.
I mean, they could have you graph it, they just couldn't refer to it as a function. They could give you that, you know, it'd be called I would call it a relation if it doesn't specifically fall into the function category. They could ask you to graph it as long as they don't refer to it as a function. Does that make sense? Like you couldn't officially, I would argue that the way this is now, I couldn't write something like f of x equals and then try and do my piecewise. Because f of x represents a function and I can tell right there it's not a function. Now, in all reality, what's probably supposed to happen? One of those points is probably supposed to be filled in is what I would guess. Okay? I mean, for what we're talking about here in terms of one-sided limits, that doesn't specifically matter. Because whether that point's filled in or not, it's not continuous. Is that making sense a little bit?
Yeah.
I mean, I think it comes down to it's probably, you know, kind of like over here. I don't see how that one could be a filled-in point on a vertical asymptote. Like, just, you know, we can cross through a horizontal asymptote in the middle, but not a vertical asymptote. So, okay. Let's look at the bottom example here. Find the points or intervals at which the function is continuous and the points at which the function is discontinuous on the interval from -5 to 10. So we're going to talk continuous. We're going to give the intervals on which it is continuous. And then we're also going to list our discontinuities. Sorry, that is the only way I can spell that word, okay? So, okay. We're going to list our discontinuities. And when we list the points at which it's discontinuous, we're also going to say a little bit about, you know, what kind of issue it is, what type of discontinuity it is. So, what are you thinking? What do we know first?
From -5 to -3.
You guys with them?
Mm-hmm.
-5 to -3 is continuous.
That'd be a bracket on the left and a parenthesis on the right. Or is that not what they're asking?
I was just checking that, honestly. -5, I have in my notes parenthesis. I guess maybe because there's not a point there.
Okay.
That's the only thing I can figure out. Okay. So -5 to -3. Why did we stop at -3?
There's a
X equals -3 is a discontinuity. Specifically, you guys use the word a whole, and it is what type of discontinuity? Okay. I'll go for both. In my brain, I was looking for removable. Although I would also I would agree that it is a point discontinuity. Does that make sense? And so my brain was looking for removable, but we could also talk about it as a point discontinuity. Okay, continuing along. Now what?
-3 to 3.
Agree? Is it okay that he kept going through -1? It's included, yes? Okay, it's not a whole or anything, so okay, it turned, but that's all right, it's still continuous. So -2 over to 3, or excuse me, I said -2, didn't I? -3 over to 3. Why did we stop at 3?
X equals 3 is asymptote.
Okay. Doesn't really show it, but based on the action of the graph, we can assume that is an asymptote. What do you know about an asymptote? Okay, it is non-removable. I should just not look at my answer key at times.
That also be considered infinite.
Yes.
Which vocab is better for the AP test?
Be familiar with both.
Okay.
I mean, it's one of those, just know what they're talking about that way. If you see those words, you're familiar with them.
Yep.
Okay. Now what?
3 to 5.
Are we with them? 3 to 5. Whoosh. And why did we stop at 5? It's another whole again, which makes it
Removable.
removable. And we again could call it a point discontinuity. Now what?
7.
5 to 7, I'm being told.
That's a jump.
We're stopping at 7 because there is a jump discontinuity. How do I have it written in my notes? I have jump discontinuity, and I do have written down that it is non-removable. And then
7 to 10.
7 to 10.
Oh, crazy?
Are you giving me y values instead now?
Yes.
Always list your intervals. When they ask you for intervals, we're always listing them in terms of x's. Because that's kind of like from left to right, what are the y values doing?
So, do we have to write anything at the bottom for that? But since it's just the end of the graph, do we not?
No, I didn't. Just like we didn't write anything for -5 because it's the in the beginning of the graph.
We're getting through a lot more than I thought we would today.
It's not that much.
That was just true.
Yeah,
Is it
the bottom.
sidetracked?
Well, the bulk of the stuff is going to end up being tomorrow's what's going to happen because those other pages are going to take a bit. Okay,
It's just talking.
the next page is really a lot of information, so we're going to talk about through some of this. Okay, so definition of continuity, more facts and theorems. So one-sided continuity. A function is called left continuous at x of equals c if the limit as x approaches c from the left of f of x is equal to f of c. And so that's what we talked about. Where was it? Right here. When we first looked at 9. Well, nope, that wouldn't be a good example. Never mind. Okay. Like right here at -5. This is one-sided continuous from the left because the limit from the left approaches -5 and it equals, what is that, -2 or whatever? So when we talk about, getting to the right page, left continuous is, if the limit from the left equals that value. Right continuous if the limit from the right equals the value at the point. Continuity. Again, this is really our big goal of this lesson, is to talk about continuity at a point. This is putting it in words. Suppose f of x is defined on an open interval containing x equals c. Then f is continuous at x equals c if the limit as x approaches c of f of x equals f of c. So that's official terminology. The limit from the left equals the limit from the right. That right there is said by the limit as x approaches c of f of x. And that equals the value at that point. So it equals the function at c. Okay, that is your definition of continuity. Okay, we have continuity on an open interval versus closed interval. Continuity on an open interval. A function is continuous on an open interval, a to b, if it is continuous at each point in the interval. Whereas continuity on a closed interval, a function is continuous on a closed interval, a to b, if it is continuous on the open interval, a to b, and the function is continuous from the right at a and continuous from the left at b. Okay, I think they're really just getting kind of fancy there. But if we think, I'm going to say here's A, I'm going to say here's B, and I'm just going to use like a traditional curve there. But if we think about this being my interval from A to B, it's continuous on the open interval, so it's continuous all the way through. And that's continuous from the right at A, so as you approach from the right at A, and from the left at B, so as you approach from the left at B. It's just saying those endpoints are connected, basically, for it to be continuous. I don't know if that makes sense or not, but that's what their fancy stuff is. Okay, we have continuity laws of some basic functions. One thing that you can always use to your advantage, polynomial functions are continuous over real numbers. So when we talk polynomials, if you recall from your algebras, are when there is just the addition and subtraction of regular terms. So you have something like x to the fifth minus 4x to the second plus 2x minus 3. So just a whole bunch of different x terms added and subtracted. That's a polynomial. Polynomials are always going to be continuous. Okay, it doesn't matter how many terms you add, they're always going to be continuous as long as it follows polynomial rules. Rational functions, such as p of x divided by q of x, continuous on its domain. What is that supposed to say? Such that q of c does not equal 0. Basically, as long as the denominator is not equal 0. So a rational function is continuous as long as the denominator cannot equal 0. Y equals 1 over the square root of n is continuous on all reals if n is odd, and continuous on 0 to infinity if n is even. Well, what are we looking at? If n is even, this is what kind of function? Like, what's 1 over 2 make it?
Square root.
Square root, right? So 1 over 4, 1 over 6. Square roots are always going to be, that's like what? Half of a sideways parabola?
Mm-hmm.
4th roots, 6th roots, those are all variations. What's like 1/3?
Leggy thing.
It's a sideways x cubed. And so that one's going to be continuous over all reals, whereas this one is just going to go from 0, 0 over. Okay. Sine x and cosine x, continuous. Oscillating up, down, right? Always continuous. B to the x, continuous as long as b is greater than 0 and b does not equal 1. That's your exponential, yes?
Yeah.
We just talked about those last week. Log is continuous for x greater than 0 because your log function is the one that does this. It runs along the vertical asymptote there. And then inverse functions, if f of x is continuous on an interval with range r, and the inverse exists.
Why is it random parentheses?
The parentheses are off where they're supposed to be. Like, I think that's what I'm trying to figure out. I think the parentheses are supposed to be here, maybe? I don't know. There's obviously, because these parentheses were supposed to be here. Oh, is mine like that? Yeah, mine's like that too, I guess. The parentheses are just off. But anyways, inverse, continuous, basically if the inverse is continuous, okay? Or the composition is continuous there. And then we have some properties of continuity at the bottom. Scalar multiple, you can multiply by a number. Sum or difference, we can add or subtract. Product, we can multiply. Quotient, we can divide. And then compositions, okay? So we will tomorrow look at example 3. So we have 3 pages left to go. Some of these examples are kind of big though. So I would like to think though, if we get in here and get going and don't mess around.
We never mess around.
Yes.
I know.
Oh my gosh, every day. We get in here and get going, we can get these done tomorrow. That's our goal. Let's focus and make it happen.